3.9 antiderivatives, and this is really kind of the last main section or collection of topics we'll be talking about this semester. We are skipping 3.8, which is Newton's method. Newton's method is really kind of a beautiful algorithm, and let me just briefly tell you how what Newton's method says, even though we're skipping it. What Newton's method is all about is, suppose you have some sort of equation that crosses the x-axis, and you want to find this point where it crosses the x-axis. But say the equation is something that's really hard to solve. I don't know, like sine of x minus x equals 0 or something like that. This is probably not. Actually, that's sine of x minus x squared plus 5 equals 0. The other one, 0, was the answer. Okay, but suppose you got something like this. It's really hard to solve. There's signs that you have to solve and x's at the same time. There's no real algebra that does this. It probably doesn't look like this graph, by the way. How do you go about solving this? Well, what you do is you can kind of look at your graph and estimate where the answer is. So you can kind of know the answer is close to it, and then you get a starting point that's nearby. And so you pick a nearby point, and when you pick a nearby point, what you do is you make that estimate increasingly better. And the way you make it better is you draw a tangent line, and then notice that wherever it crosses will be closer to the actual answer than the point you started with. So you start here, get your tangent line, you get a new value, and there it is. And now we're going to get another tangent line, and here's our new value. And now we're going to get another tangent line. And notice every time you do this, your values are getting closer and closer and closer to the point. And this is the idea of Newton's method. You follow this process where you use tangent lines to get your values closer and closer. So this involves derivatives. And this is actually it's actually a really good method, and your calculator, when your calculator finds zeros or anything like that on it, the calculator is actually using something pretty close to Newton's method. So the calculator doesn't know where the zeros of functions are, but it has programmed into it this algorithm that it does it over and over and over again. It's really an interesting section. It's too bad that we're skipping it because I really like it. Okay. But at any rate, what we are talking about is antiderivatives. So what I want you to do is read this question and pause your device and try it out. So if f prime of x is x squared, what is f of x? So notice I'm not asking the derivative. I'm saying if we know the derivative. We have some function right here. We have some function right here. And I put a box over it, so we don't know what it is. And then I took the derivative of it, and I know that I got x squared for my answer. The question is, what did I start with? Okay, so pause your device right now. Try this problem and see how successful you can be. All right. Hopefully you pause your device and you tried some different things. Often people will try like 2x, but notice 2x, the derivative, right? 2x, the derivative is 2. It's not x squared. So we have to somehow go backwards from what we've normally been doing. Well, it turns out that what we should do is we should think that every time you take a derivative, the power gets one smaller. So in order to get x squared, you have to start with x cubed. Okay? But x cubed isn't quite right, because if we took the derivative of x cubed, we would get 3x squared. So what do I need to do? I need to somehow cancel out that 3. Well, the way to cancel out a 3 is to multiply it by 1/3, which is just fine, because if you multiply by 1/3, then you have an equation that 1/3 x cubed becomes 1/3 times 3x squared, and that 3 and that 1/3 cancel out, and you get just x squared. All right, so this was the function that gave us the antiderivative. So what we call 1/3 x cubed the antiderivative of x squared. So let me write this down. 1/3 x cubed is the antiderivative of x squared. So what is an antiderivative? And by the way, this is the point in the semester when you look at me and you go, hey, I'm antiderivatives. Okay, that was meant to be a bad joke. Maybe someone at home laughed. Usually this dude's just groan, just like my children do when I tell jokes at home. Okay, but what is an antiderivative? An antiderivative is just where you try to do a derivative backwards. So you start with the derivative and you try to figure out which function it came from. Well, it turns out that there's a lot of functions that we kind of can know what the answers are. So let's just write all these answers down as we have them. And so if you have a constant, how do you get a constant? Well, if you get a constant, you just take that constant times x. Because you know, like if you have 5, then you have to take the derivative of 5x to get 5. So we're just doing the derivatives backwards. How do you get just a plain x by itself? Well, the answer is an x squared. But just like here, you can't just do an x squared. You have to do a 1/2 x squared. Because if you take the derivative of 1/2 x squared, you get 1/2 times 2x, and that gives you x back again. And what you'll notice is there's a general pattern that seems to be forming. 1/2 x squared came from x. 1/3 x cubed came from x squared. And it turns out that whatever your power is, you raise that power by 1, and then you divide by whatever that new number is. So, for example, if I were to have, say, x to the 10th, my antiderivative, I would raise it to one number. So instead of 10, I'd make it 11. I would add 1, and then I would have 1/11 out front. So whatever your number is, you just keep raising it like that. Okay, so how do we do a square root? Well, it turns out square roots work the exact same as always. And square roots, we would have a 1/2. So we'd have to add 1 to the 1/2, which becomes 3/2. And then we divide by 3/2. So we get 1 divided by 3/2. And instead of that, I'm going to flip that fraction, and I'm going to write it as 2/3 x to the 3/2. By the way, there's one number that doesn't work for this. So this one right here only works if x is not equal to 1. So 1 is or negative 1. So x equal to negative 1 is a problem. Let's see why x equals negative 1 causes a problem. So what if we have x to the negative 1? What do we get when we do this process? Well, you add 1 to it and get 0. And then in front, you have 1 divided by 0. And we all know that this is really, really bad, right? By the x to the negative 1 is 1 over x. So we're not allowed to do 1 over x. We can do every other equation except 1 over x. We can do 1 over x. But that will be something that you do in Calculus 2. So this will be something we learn in Calculus 2. Do you want to know what the answer is? The answer is natural log. So you have to use a natural log to solve these problems. But that's not for this semester. That's for the future. Okay. Okay, sine and cosine. Well, what I know is that the derivative of sine is cosine. So sine of x matches up with cosine of x. And the derivative of cosine is negative sine. So cosine of x should match with sine of x, but cosine gets the negative sign. Now, I always have to think about these negatives because they're backwards of what they were when we took derivatives, which makes sense, right? The derivative of sine is cosine. The derivative of cosine is negative sine. Well, now they're the same, except the negatives are backwards, but that's because antiderivatives are going backwards from what derivatives are. So sine becomes negative cosine. Cosine becomes sine. Secant squared of x. Secant squared of x, we know that the derivative of tangent is secant squared, and that's just one you have to know what the derivative is. And secant x, tangent x, we know is secant x. Real quick observation, there are lots and lots of equations that we just can't do the antiderivative of. And there are lots of things. So unlike derivatives, where really any combination we make with multiplication, division, any combination we make, we can find a derivative. That's not true for antiderivatives. It is real easy for me to make combinations of equations that you can't do with antiderivatives. Let me just give you a few things that cause trouble. Sine of x squared causes a lot of trouble, right? So this seems simple that we just have a sine and an x squared inside, but this becomes really, really hard. Or similarly, sine of 1 over x causes us a lot of trouble. Some of these, there are solutions, but they're not very pretty. They're not things that you learn kind of in Calc 1, and really they take the most advanced techniques. Even something like tangent of x, you can do tangent of x, and you'll do it in Calc 2, but right now we don't have an answer to it. What you have to do is you have to make it sine over cosine and do something like that. And for those of you who've been through statistics, e to the negative x squared is the normal distribution. And this is like the most important equation in all statistics. And it is the equation we most want to find an antiderivative of. And it turns out that we just can't do that. So this is one that has no antiderivative written in terms of simple functions that we're aware of. Its antiderivative is not in terms of simple functions. Okay, that doesn't mean it doesn't have an antiderivative. It just means an antiderivative we can't write down using the types of notations that we have in our form. Okay, let's come back, and I want to make an observation about that very first problem that we did, though. And it was if the derivative was x squared, our original function could have been 1/3 x cubed. But there's actually a bunch of other functions that also give us the same solution, that also give us x squared. And the way to come up with this is to recognize, well, we could add a 0 on the end of here, and that wouldn't change our problem. What has a derivative that's equal to 0? The answer is any constant. So 1/3 x cubed plus 1 would also have a derivative that's equal to x squared. 1/3 x cubed plus 2 would also have a derivative that's equal to x squared. So what we do is we have what we call the general form of the antiderivative. And the general form is we put a capital C on the end. And the capital C on the end is just to make a point that we could add any constant to this problem and still get another antiderivative. And it doesn't matter what the constant is. Usually we think of it as 0, but sometimes 0 isn't the number that we want. Sometimes that number is a different constant. So the general form is f of x plus c. So we always add this plus c. And so when you do your homework, when you go into Calc 2 and you're doing these things every day, don't forget your plus c's. The plus c's matter. So add a plus c on the end when it asks for the general form of the antiderivative. And by the way, this has kind of a nice geometric meaning. So the geometric meaning, if you think of our x cubed, our 1/3 x cubed, looks something like this. And we can see that its derivative, well, what's its derivative? The derivative over here is positive and 0 and positive. So the derivative is positive, 0, and positive. So the derivative looks something like that. So you can see the derivative is that x cubed. But what you notice is, if I were to take this whole picture and move it up a little bit and draw the same picture, it would have the exact same derivative because where the height of the function doesn't affect its derivative. It's only the slopes of the function. And so if I took that whole thing here and drew it like that, these are all meant to be the same picture, just lifted up or lifted down. I know I'm struggling with my drawing abilities. But what you can see is that adding a constant to the 1/3 doesn't change its derivative. So what we have is we have a bunch of equations, and the equations are just shifted up and down, and shifting them up and down doesn't change its derivative. Okay, well, what we need to do now is we need to tackle a bunch of problems. So what I want you all to do is I want you all to get some practice trying to find some of these antiderivatives yourself. So again, pause your stream and try 3.33. And hopefully you can make some progress finding the antiderivatives of each one. On the second one, you're going to have to do a little bit of algebra first. So see if you can make that algebra work out. Okay, sorry if you're back. Just be patient with me as I write this out. All right, so there's my function. Now I want to find the antiderivative. By the way, traditional notation is we use this for our derivative, and we often will use a capital F to represent the antiderivative. So when you see the textbook or you see me write a capital F down, what we're trying to say is think about the antiderivative of this equation. Okay. Well, in order to find the antiderivative, the first thing I'm going to do is I'm going to write all these with powers in the exponent. Oh, sorry, this was a square root of 2. I'm going to write all these with powers in the exponents. So that is going to be x to the negative 2. This is going to be 4x to the 1/3. And this one is going to be, let's just leave it as the square root of 2. Okay. Now what is our antiderivative going to be? And so our antiderivative is, well, you simply follow our formula, and we know that x to the n goes to x to the n plus 1, 1 over n plus 1. By the way, some people will write it like this, divided by n plus 1, and that means the exact same thing. So you can divide the x by the n plus 1 or write it as a fraction out front. It's the exact same either way. Okay, so I'm going to write x to the negative 2 plus 1. Negative 2 plus 1 is negative 1. And then we'll have 1 divided by negative 1 out front. Okay. Now here I'll have 4, and then I'll put x to the negative 1/3 plus 1, or 1/3 plus 1 is 4/3 when I add 1 to that. And then I have 1 over 4/3, or 3/4 as a fraction. So that becomes 3/4. And now, what do I do with that square root of 2? It's tempting to make it a 0, but it's not, because we're not doing derivatives, we're doing antiderivatives. To do an antiderivative, you multiply it by x. The square root of 2x would be just square root of 2 when we do that. Let's clean all this up just a little bit, just to make it look a little bit nicer. So this is going to be negative x to the negative 1 plus, these 4's cancel, 3x to the 4/3 plus the square root of 2x. And so this looks like a pretty good answer here for our problem. All right, let's try that second one. So if you haven't already, pause your device and try part B. I guess I didn't put A's and B's on them, but try it anyway. Our second one, we have f of x equals to x squared sine of x plus 1 over x squared. Well, this is a problem where we need to do a little bit of algebra. And the way I'm going to do the algebra is I'm going to unadd the fractions. So to unadd the fractions, we'll get x squared sine of x over x squared plus 1 over x squared. And then when you unadd these fractions, you get just sine of x. And then over here, you've got 1 over x squared, which is x to the negative 2. Now, I'm in really good shape to take my antiderivative. And so my antiderivative is sine of x is cosine, but it's not cosine, it is negative cosine. How can I tell? I say, well, what's the derivative of cosine? The derivative of cosine is negative sine, so I need this negative on here. Negative cosine, and then we've got plus 1 over negative 1 x to the negative 1. This is the same problem we did right here. So what if I just make it 1 over cosine minus x to the negative 1? And I should have added one more thing on both of these answers. I should have added a plus c to make the general form. So this one should have a plus c on here. Did you forget it also? Well, try to be real careful not to forget. So let's put our plus c's on our answer every time we do them. Okay, now we're going to talk about the plus c's for just a little bit, because we're going to talk about what happens when we have a plus c in exercise 3.34. So in 3.34, what we're going to do is we're going to keep track of those plus c's, and if you're given just a little bit more information, you can actually figure out what that constant is. So notice that picture I had earlier, where I had all of my functions, where I had this function right here, and then this function right here, and then this function right here. Well, the answer is, if I tell you one spot that the function goes through, so if I say I know the function goes through that one, that spot, well, it turns out there's only one of these equations that works, and it would be that equation right here. I missed, but it would be that equation. And so if I give you one point, then you can use that point to find out what your C is going to be and which one of those graphs you're going to be using. So that's what we're going to be doing right now. We're going to be looking at these and figuring out what is the C for our plus C problems. All right. Okay, so let's do 3.34 and see what we get. So find f of x for each of the following. So we have f prime of x. F prime of x equals sine of x minus x cubed. But we're given one extra piece of information, and that's that f of 0 equals 3. And so we're going to be able to use this to figure out what our C is when we solve our problem. So let's do this problem. Let's find our antiderivative. We're ready right now. we can just say f of x, because this has a prime on it. So the antiderivative of sine is negative cosine, like we did just a moment ago. And x cubed is going to be x to the fourth, and we'll have a 1/4, and we'll do plus c. But now what I'm going to do is I'm going to take this part, and I'm going to plug it in to see what happens. So I'm going to plug in 0 for x, plug in x equals 0, and then set the whole thing equal to 3. Because notice that, so that means that if I get negative cosine of 0 minus 1/4, 0 to the fourth plus c equals 3. Now what I can do is I can solve for c to figure out what that constant should be. Cosine of 0 is 1, so I've got negative 1. This is all 0 plus c equals 3, and so c has to equal 4. So since c is 4, I can now write down nicely and neatly what my final answer is. So my answer is f of x equal to negative cosine of x minus 1/4 x to the fourth plus, and c is 4, so plus 4. So now, instead of having a plus c for my answer, I know what that constant is. I know which number gets added on, and it's the number that makes this equation true. So what you can see, oh, sorry, this is 3.34. So what you can see is we can use this information to figure out our c's. Now for the next problem, by the way, you should go ahead, you should be trying these ahead of me, so you should be pausing your device and trying these before I get to them. But for the next problem, we're going to do this twice, because we're not going to start with the function, we're going to start with the second derivative of the function. So f double prime of x equals 1 over x cubed, or x to the negative 3. And then we're given two extra pieces of information. We're given that f of 1 is 0, and f prime of 1 equals 0, and f of 1 equals 1. So we're given those two pieces of information. With these two pieces of information, we can solve out what's going on in this problem. So first, let's do the first antiderivative. And we know that f prime of x, so we went from double prime to prime, so we took one antiderivative right here. We do our rule, we add 1 to it, so that's x to the negative 2, and we've got 1 over negative 2, x to the negative 2, plus c. Now, let's come over here, and let's figure out what is that c going to be. Well, I'm going to use this equation to figure it out. So I get negative 1, or 1 over negative 2 times 1 to the negative 2 plus c equals 0. This all ends up being negative 1/2 plus c equals 0. So c is simply 1/2. So that means this derivative equation is the equation f prime of x equals negative 1/2 x to the negative 2 plus 1/2. So that's my first one. Now what do I have to do? Now I have to do it all again, and this time I'm going to use this equation to figure out my next constant. So I'll do f of x equals, well, let's see, I've got negative 1/2. X to the negative 2 is going to become negative 1, and I'll get a 1 over negative 1 plus 1/2 x. Notice there's no x there, and x shows up because when we take a derivative, a 1/2 x becomes a 1/2, and then plus c. All right, so now let's use this to figure out what this last c is. And so this negative and this negative cancel, so I've got 1/2, 1 to the negative 1 plus 1/2 times 1 plus c equals 1. And let's see, that gives me a 1/2 plus 1/2 plus c equals 1. 1 plus c equals 1, so c has to equal 0 in this case. So that means this c is 0, so that tells me what my final answer is. My final answer is negative 1/2, positive 1/2 x to the negative 1 plus 1/2 x. And there we go. And so I had to do, in this case, I had to do two antiderivatives. I had to do an antiderivative from f prime to f, and then I had to do an antiderivative from f prime, or f double prime to f prime, and then f prime to f. And then twice I had to go figure out what the constants were to plug the constants into my problem. All right, I'm gonna pause the video and make a second video. So this kind of gets you through most of the homework assignment. But there are a few problems where I want to think about the relationship between derivatives and velocity and acceleration, and this is going to help you think about physics. And so I will set that up, and then I'll come back and we'll do a second video starting on page 85 where we talk about some physics applications of these problems.